This is a modern cargo ship at full speed. It is a massive block of steel carrying tens of thousands of tons of forward momentum. On land, stopping relies on a mechanical braking system. You push a pedal, brake pads clamp a rotor, and the tires press against the road surface. That system uses static friction to convert forward kinetic energy into heat energy, effectively anchoring the vehicle to the earth. A cargo ship carries exponentially more kinetic energy, but it operates in a fluid. A steel hull offers no static friction surfaces for a mechanical brake to grab. There is no way to instantly arrest that much forward momentum. To stop safely, ship navigators must artificially manufacture hydrodynamic drag, and they must do this while avoiding engine maneuvers that completely destroy steering control. Mastering maritime deceleration requires a navigator to solve a complex fluid dynamics problem, using precise inputs to bleed energy from tens of thousands of tons of steel. Under normal conditions, navigators perform a controlled speed reduction over miles of open ocean. By slowly dialing back the main engine, the natural drag of the hull passing through the water eventually overtakes forward thrust. Crucially, the propeller must keep turning forward throughout this entire reduction. As this image shows, the rudder sits directly behind the propeller. It is the vessel's only steering mechanism, and it requires a continuous flow of water to function. If an obstacle appears suddenly, with no room to slow down, the crew must aggressively manufacture drag. The first emergency option is high-frequency rudder cycling. By rapidly oscillating the rudder from side to side, the crew breaks the smooth laminar flow of the water. This creates localized turbulent drag wake zones at the stern, bleeding energy without altering the ship's heading. For more intense deceleration, pilots use low-frequency rudder cycling. They intentionally induce a severe turn, letting the ship swing 30 to 40 degrees off its path before correcting back. Angling the massive steel hull against its own forward momentum turns the entire broadside into a drag multiplier. Low-frequency cycling and full helm turns can arrest a massive vessel's momentum in just 5 or 6 ship lengths. In a fluid environment, the hull itself acts like a massive parachute. By precisely angling that geometry, navigators convert directional momentum into pure hydrodynamic resistance. The final emergency option is the crash stop order, signaled by moving the engine telegraph to full astern 3 times. Most commercial ships use a fixed-pitch propeller bolted directly to a massive diesel engine with no gearbox. To perform a crash stop with this hardware, engineers must stop the direct drive engine dead and restart it rotating in the opposite direction. Even if restarted, blade physics work against the ship. Fixed-pitch blades are optimized for forward motion, using a sharp leading edge. Reversing forces the blunt trailing edge to cut the water. Thrust efficiency immediately drops by up to 50%. Most dangerously, pulling the engine into reverse creates a massive cavitation void. This acts like a vacuum, sucking water away from the rudder. Without water flowing over its surface, the rudder becomes useless. The ship loses 100% of its steering capacity. A crash stop with a fixed propeller is a trade-off. You gain highly inefficient deceleration at the cost of total directional control. To solve the inherent mechanical limitations of reversing a fixed-pitch engine, engineers developed the Controllable Pitch Propeller, or CPP. Unlike a fixed blade, a CPP uses internal hydraulic hubs to twist the angle of attack, or pitch, of the blades independently. During a crash stop, the main engine never stops rotating. Instead, the blades smoothly pivot past the zero pitch point. Because the entire blade twists, the sharp leading edge remains the leading edge. The propeller simply catches the water on its opposite face. This generates instant, massive reverse thrust without shutting down the engine or placing catastrophic stress on the drivetrain. This continuous rotation does create a specific handling quirk called transverse thrust, or propeller walk. Because the propeller is always turning, even at zero pitch, it constantly throws water sideways against the hull. This lateral force pushes the stern sideways at slow speeds. However, the CPP remains the most elegant mechanical solution, decoupling engine rotation from directional thrust to deliver instant deceleration while retaining steering capacity. These emergency capabilities are legally mandated by the International Maritime Organization. During sea trials, every vessel must prove it can execute a full crash stop and come to a halt within 15 to 20 ship lengths. If the CPP is more responsive and safer during an emergency, we must ask why it isn't standard on every commercial ship. It is a question of naval economics. Fixed-pitch propellers are simpler, lighter, and more durable. They are significantly cheaper to maintain over decades of operation. Most importantly, a fixed propeller can be flawlessly optimized for one continuous cruising speed. For long-haul transport, its fuel efficiency remains mathematically unmatched. The physics of maritime deceleration is a calculated compromise. Global shipping accepts the limitations of a crash stop in exchange for the raw economic efficiency required to move tens of thousands of tons of steel across the world.